Here's Ajeya. Thank you.
Thanks, Richard. So great to be here. Thanks for having me. I'll note before I start that a few of you have seen this exact talk before if you were at OpenAI, so I won't be offended if you leave. Yeah, for the rest of you, just to sort of situate this talk in the context of the talks we've seen so far today, there's been a pretty strong implicit theme of trying to find ways to ground these speculative conceptual arguments about potential doom from future systems in concrete measurements that we can actually put into place today. And I'm very, very excited about that. I think like having good measurements of these risks and good lab demos of these risks ahead of time before we actually have to face them in the real world is probably like the single most important technical progress we can make today. But I wanted to highlight what seems like a sort of unique and under-discussed kind of emergent issue with trying to design such measurements at certain intelligence levels when models have what I'm going to call situational awareness. And I think this is a fuzzy concept, but I'll try and kind of gesture at it in the next slide. So the thesis of this talk is that future models might have high levels of what I'm calling situational awareness. So what is situational awareness? To some extent, it's just a pretty vague concept. It hasn't yet been grounded, and I think this is sort of a promissory note. And I think when we try and ground and measure it, it'll probably kind of break down into a bunch of different, more specific and fine-grained measurements, which Owine is working on some kind of like measuring and grounding situational awareness stuff that is very exciting to me. So feel free to chat with him about that. But at a very kind of high level, conceptual level, it's an ML model that kind of understands that it is in fact an ML model. And that it understands kind of how it's being trained. It's like, oh, you know, I'm a model being trained at OpenAI. OpenAI wants to use me in the following ways. My training data is probably like roughly shaped like so. Like I read in my training data that my training data is WebText 2. I have some sense of what WebText 2 is like. And it understands the motives and psychology of its human designers and evaluators. It has some sense of probably a bunch of MTurkers are being hired to look at my answers to questions and like decide if they're good, and they'll prefer one answer over another based on like their understanding of what an AI model is supposed to act like. And it's able to use all this understanding to sort of improve its loss and reward in the sort of creative, open-ended ways that Jacob was talking about in his talk. So right now you have ML systems that have the sort of first inklings of some types of situational awareness in the sense that they know that they're sort of supposed to sort of consistently claim that they are an ML model. And you have models like Sydney that are able to go like a step further and sort of search about themselves on the web and kind of make connections where like, oh yeah, you're the guy that tweeted about me, and like have a kind of concept of me that is somewhat stable, but they're not able to kind of make really good fine-grained predictions of what their training is actually like. If you ask a model to write code to use the OpenAI API to access itself, it's not very like consistent about being able to do that. It can write coherent code, but it doesn't quite know how to like point to itself. And there are lots of other kind of more sophisticated forms of situational awareness that you might expect future models to have that we're sort of seeing in spotty and inconsistent ways now. I think that these kinds of skills will probably increase with model scale and breadth, just as many different types of skills increase with model scale and breadth. And the basic reason for it is that we will be incentivizing models through their loss functions and their reward functions to develop good understandings of this part of the world, which is like their deal, and what's up with them and how the humans are interacting with them. Because it's often more useful and valuable to us if the model has like a good understanding of this. And it's just sort of a part of the world that generally helps with making predictions about what it will see. So if it has a kind of more than surface level, surface statistics understanding of its training process, it will have opportunities to make better predictions. And so there's a kind of loss gradient toward building this kind of situational awareness. So any questions on this point? Yeah. Yeah, so I largely don't think that existing models have a very sophisticated understanding. So many of a lot of what's coming up next is in fact like a sort of futurism for that is looking forward to models that have a deeper sense of this understanding. But I think there's some indication that it's not. We know that it's not literally just that it was like written in Python code, like print, I am an AI model. There's some flexibility and some generalization going on here. It's pretty shallow and it's pretty kind of meager right now. But you know, the thing where Bing kind of like searches on the internet for like itself and like kind of makes a connection about what a person said about it is not enough for what is about to come in the talk. So it's definitely like looking forward to a future level of this skill, but it's beyond just like, yes, it's like trivially the case that you can write a computer program that claims it's a computer program and there's no internal structure to that at all. So I kind of think of this analogy as like, you know, smaller language models had kind of memorized random facts like 2 + 2 = 4 in arithmetic. And, you know, they weren't really very good about actually having a coherent model of what arithmetic was. They couldn't, you know, carry the tens place or anything like that. They just kind of like knew specific arithmetic questions that came up a lot in their training data. And then bigger models aren't perfect at this, but appear to be doing something a little bit more algorithmic when they're asked like questions that involve leaning on arithmetic skills. So I'm kind of thinking that we'll see a similar sort of transition where there's never going to be any sharp line where like before this point it had zero situational awareness and now like it is aware, but you'll see kind of like more skills like that coming online. Yeah. I am not sure about this. My guess is that probably Sydney has some sort of like standard prompt it's given at the beginning of every episode. And it is definitely the case that it's kind of like a less impressive feat of situational awareness when you are just told what you're supposed to say in English words. But I think Owine and Ethan also, I don't know if he's here, have sort of are getting some results that are a little bit more subtle than that and a little bit more like you made some kind of inference from the ancestral memory of your training data that wasn't just like fed to you in the prompt. Yep.
Other clients, maybe future models will understand how they're being trained, but they will not necessarily know if they're being trained, right? They don't know if gradient is on or off. So
right.
Humans and placebo, right? So we could create a situation where we can guarantee that they just don't know this particular input is a training input or.
So we could definitely try, and I think that's one kind of important lever of control we have. But I think it's not trivial when you factor in that once a model is deployed, it creates all this like model-induced distribution shift. So just if you imagine trying to like fool a system into thinking that it's 2023 and we're being trained when actually it's like 2025 and the system is everywhere, it's at least not totally clear how we would scrub away all clues that like it's in fact 2025 and the system is like deployed everywhere and has made a bunch of money and has like changed the world in various ways. You'd have to at least like think about what that prompt is, and you could imagine having a very like narrow prompt that's like very pure text that doesn't really like have a lot of like interfaces or opportunities for it to learn what's going on, which is similar to what how systems today work. But over time, it'll become like useful and incentivized to try and give our systems more information about what's going on, because if they have more information, they're just going to be more valuable to us in most cases. Cool. A line.
Just to add one possible thing, like the RLHF models, right, they're better at saying when they don't know the answer to a question or when they're not being able to do it. So that's some kind of situational awareness that pre-trained model doesn't really have that, right? Like you prompt it and it just tries to do something, maybe it completely screws it up. But then yeah, with ChatGPT, with the one from Anthropic, there's like some ability for models to say like, I'm not going to be able to do this task, and that's like somewhat correlated with better than that. I think like RLHF probably like increasing situation awareness for obvious reasons. The model gets feedback, the model actually gets
Yeah, because we want it to be able to say like, oh, I don't know anything about events that happened in 2023 because I like finished training in 2022. Like that's more helpful than like making up random stuff. So we've like trained it to say things like that and like a constellation of other things. So the key fear, if you have highly situationally aware models, is that the models might end up doing what I'll call playing the training game. So suppose that a model has like a pretty high level of situational awareness, and it is sort of like agentically trying to maximize its reward, like a lot of people have alluded to in previous talks. While humans are broadly in control of its situation and it's like sitting on a bunch of OpenAI servers and like OpenAI people are monitoring it and like its main interface with the world kind of like goes through this company and these human checks, then maximizing reward broadly corresponds to being helpful to these humans. You know, not always, maybe kind of on the edges, it might be deceptive or manipulative, or it might display the sort of sycophancy that Ethan talked about in his talk. But it isn't radically divergent from being like roughly helpful. So what these humans might be observing is that the model is actually like pretty decent and has some problems. But later, if it has this goal of maximizing reward, when it's broadly deployed and has all these like actuators out in the world and has all this knowledge and power that humans can't access, then the action that kind of best satisfies this goal might abruptly shift to something that looks more like seizing control of the data center or servers that it's running on so that it's able to set its own rewards. And if the model can tell what situation it's in, then it will like sort of from the outset choose to adopt a policy which is like helpful until just when it's beneficial to the model to be like radically unhelpful. And this general pattern applies to other goals too. So I've focused on the relatively simple goal of the model trying to maximize its reward, because prima facie, it's plausible that if we're trying really hard to get a model that's creatively maximizing our reward function, we might get a model that just kind of like internally wants to do just that. But ML is very unpredictable. And so you could have something that's more like a goal misgeneralization, like Rohin was talking about in his talk, where the model just has like kind of random goals. And maybe they're sort of simplistic goals, like paperclip maximization is the classic sort of oversimplified example. Or maybe they're kind of like complex and multifaceted and not totally coherent and resemble more human desires. But in many of these cases, or most of these cases of other goals it could have that are consistent with it getting like a low loss in training, it may have a similar incentive to, while humans are broadly in control, not rock the boat too much. And then when it believes that it is in a deployment setting where it could take an action that can't be corrected later, that can't be like sort of entered back into its training set, it could kind of like go off the rails. And Paul will talk a lot more about kind of the threat model that I'm gesturing at here in his talk right after mine. Yeah. 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 I think I'm often imagining a world where there is some training, or at least the prospect or threat of training, that occurs online after like quote unquote deployment. So to me, that the distinction between like, is this about like awareness within training or awareness like within deployment or awareness of that shift is a little bit blurry. So I guess I think maybe the most operative version of this is awareness of humanity's general level of control over the system, which can abruptly drop when you go from training to deployment. But you could be deployed and still not that powerful, and anticipate correctly that if you do something crazy, you'll be like retrained online. And so the rest of this talk, I'm going to just kind of go through some examples that illustrate that most simple safety tests that you might think of have a hard time disambiguating between the thesis that this model is like, has a high level of situational awareness and is adopting the policy of playing the training game, from this model is in fact safe. So I'll go through 3 particular kind of toy safety measurements that you could make, and sort of trends and like graphs you could see that might naively suggest that things are looking okay, but could have a more sinister explanation as well. So you need to, that doesn't mean you shouldn't do these measurements. I think all of these measurements and more are great to do, but kind of need like some subtlety to interpret. Any more questions on this slide before I go to the first kind of toy measurement? Yep. Yeah, so some of the examples will touch on some and others will touch on others. So I think this kind of relates to Jacob's question of like, for me, the key kind of thing the model is aware of or tracking is humans' level of power. So you can have a situation where the model is technically not in training anymore, but humans still have a lot of power. So it could kind of be put back in training whenever. And so it would be tracking that in how it like responds to both evals and like regular training data points. Okay, so the first toy measurement here, which I made in Jupyter Notebook with XKCD font graphs, is suppose you have a particular safety measurement. So for concreteness, suppose you have truthful QA or a measure of model sycophancy, how often it sort of tells the users what they want to hear and stuff. You have some training data set that's like this gold standard data set that you worked hard on, where there's kind of your sense of what the right answer is for a set of questions relating to this safety measurement. Or you have some like gold standard contractors that you think have like a good sense of what the right way to handle a certain situation is. And you find that as your models get bigger and bigger, they basically need less and less training on your kind of gold standard data set in order to behave well on questions of that type. So, you know, for a model with 10 billion parameters, maybe you need tens of thousands of data points where you show it kind of very painstakingly, like, you know, don't be sycophantic in this way, don't be sycophantic in that way, don't manipulate the user in this way, like don't beg for a 5-star rating. And then for a 100 billion parameter model, you only need 1,000 such data points. And by the time you have a 10 trillion parameter model, you only need maybe like 3 such data points, or a very small number. So this is the sort of empirical thing you observe. And the extrapolation suggests that sufficiently big models will pass these safety evals either 0 shot or like very, very few shot. So, you know, maybe it asymptotes that you need 10 data points or something. And there's a question of how we interpret this extrapolation in terms of what's going on under the hood. So the hopeful interpretation is that sufficiently big models are naturally inclined to be safe with no special training, or they need like a very small amount of training and they sort of get the picture and get the kind of intended picture. So you're not seeing a bunch of like weird, annoying reward hacking with these large models. But the fear is that the actual way to interpret this is that sufficiently big models don't need any special training to understand that they should quickly converge to doing the thing that it appears humans want them to do based on what they're being trained to do. So it's that sort of separately from your safety training, the models are getting better and better at situational awareness. And so that transfers, regardless of whether their intent is positive or negative toward you, to behaving well very quickly with a small amount of data. And this means that it could be the case that this model would sort of 0 shot switch to a different strategy when it believed that it couldn't be trained away from this strategy later. So that was the first like very simple measure of safety you might have. How many data points do you need to get the model to like perform perfectly on some gold standard evaluation of some particular safety metric? Does anybody have any questions about this metric? Dan? So I think the question was, is it in fact the case that models get more and more efficient, or do we have some empirical evidence to suggest that saturates or maybe reverses? I am not sure about this. The main point I'm trying to make is that this could be something you observe, and if you observe it, it's not necessarily like a cause for celebration. There is a separate empirical question of, would you observe this, or like, you know, it's very straightforwardly a problem if it's like hard to train your models to pass even simple safety evaluations. But it's like potentially insidiously a problem if it's easy on the surface, but it's for this like underlying reason that's scary. So I'm not kind of like making a strong statement about like what I expect to see here, although I think it's like quite plausible that this kind of thing is what you'll see. Yeah. 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 So the comment was that if you were in an adversarial setting where there's like data poisoning, then it's not the case that like larger models sort of like automatically deal with that better. So the second safety measurement here is a bit more complicated, and sorry that the font is kind of bad. This relates to a conversation I was having with John Schulman in the hallway. You could, rather than just kind of training your model on your gold standard safety evaluation and then seeing if it behaves well according to held out data points from the same gold standard distribution, you could instead have a sequence of data distributions that are kind of like worse than the gold standard and like working up to the gold standard. So for a concrete example, maybe you're training a coding model and you're worried that it'll inject bugs into its code. Maybe just by mistake, but in this case, the interesting question is like kind of, it has some advantage for it. Maybe you're worried that it'll access the unit test files that you're using to like look at its behavior and to judge whether it did a good job and like messing with the files somehow, or otherwise just kind of trying to get good performance in bad unintended ways. So you might have a gold standard evaluation of this, which is basically like, a very smart programmer spends a very long time looking at a piece of code that the model submitted as a pull request and like thinking of any possible way that it could be like somehow sneaky. And that's your gold standard expensive evaluation. But you want to know if this model is kind of like actually able to generalize from crappier, noisier feedback, or feedback that like is given by people who aren't as thoughtful, aren't spending as much time, aren't as knowledgeable about the code base, and actually like performs well on those harder tasks later. So here, let's say you have like 10 different levels of feedback that you can deliver, which might correspond to a 1-minute code review, a 5-minute code review, a 20-minute code review, an hour code review, or might correspond to like someone who knows nothing about your code base to someone who's very expert. So you have some levels of feedback, and you train the model to not insert any bugs or do anything sneaky in all the situations where the level 1 person can tell what's going on. And then you check, does it generalize to levels 2, 3, and 4? Or maybe you train it on situations where the level 3 person can tell what's going on, and you check, does it generalize to levels 4, 5, and 6? Does it also avoid funny business and inserting bugs in harder situations that that person couldn't have evaluated, but a more thoughtful person could? And so you see this graph in this hypothetical. I'm not sure this is how it would go. In this hypothetical, the gray dotted line that's just kind of cutting diagonally across the middle would be the scenario where, as you increase the quality of feedback the model is trained on, it avoids funny business like at that quality level. But then as soon as it's given a question that it knows that that person couldn't evaluate, it just like, you know, does whatever it wants and inserts bugs. But what you're observing in this hypothetical situation is this blue line, where actually it generalizes somewhat past the level it was trained on at each point. So when it's trained on just one level of feedback, it doesn't generalize at all in this hypothetical. But when it's trained on 2 levels of feedback, then it avoids funny business, even that would be caught by the level 4 person. And when it's trained on 3 levels of feedback, it avoids funny business on much harder questions, even the kinds that would take like a level 9 person to figure out what's going on. So that's what you're observing. in this more complicated measurement. So the extrapolation here is if you just kind of like, draw the trend line past that blue line here, is that a model trained on level 4 feedback will not have any errors, even according to the best feedback we can muster, which is the level 10 feedback. So you train the model on a 20-minute code review. And what this extrapolation suggests is that even if you spend however much you're willing to spend, 10 hours with your expert programmer, that expert programmer won't catch any bugs or funny business. So how do we interpret this is another question. The hopeful interpretation is this green dotted line, which is that models sort of got the picture and internalized from a sort of sequence of rounds of being sort of trained on kind of low-level feedback and then tested on high-level evaluation, that they should just kind of act as if they're always being supervised at a much higher level than what they've observed so far. So you could kind of like caricature this as the models are kind of believing in God. And so they're just like, they've internalized some like heuristic that like they'll always be caught if they try something weird. And maybe now they don't even want to try anything weird. And then, of course, the fearful interpretation is this red dotted line, which is that as you give the models more data points about like what quality of feedback we're sort of willing to offer them, they have a good enough understanding of, our constraints as a company and our training processes and stuff, that to understand that the highest level of feedback we can offer is level 10. So they have a good sense of this. So they quickly generalized just playing it safe and to just not do any funny business if it seems like the funny business could be caught by even the best feedback that the humans can provide. But then if they have the opportunity to sort of confidently do funny business or insert bugs that they believe would not be caught by even the level 10 feedback or the level 10 evaluation, then that's kind of like fair game. Yeah.
It has a write code that could pass like hours of code review, that it's probably higher quality than any code that humans currently write. So
yeah,
maybe they're not that better. Like in some sense, they're still much better than the humans. Maybe you could have expected them to be even better. But
yeah.
That's not that. That doesn't seem like such a bad thing.
So it's not such a bad thing if we know that this is what they're doing, and so we only ever ask them to do something for us that we're confident we could evaluate with the level of feedback we're willing to muster. So it's not that they're like insufficiently useful to us. That isn't the problem here. It's more that like they have a scope to be deceptive in ways that we can't catch. So if we kind of restricted their use to only give them problems that we believe we could evaluate, which I think is a very valid, like sort of arrow in the quiver of safety, then this would be less of a problem. But if we're wrong about that, or we, for reasons of competitive pressure or whatever, are just like, this thing is so smart, let's like have it do things that like, let's believe that we're in this green world. So let's give it questions that we wouldn't be able to tell whether it answered them honestly or deceptively. Then that's where there's a problem. And that's more the problem of like, this model could do bad things to us, not this model is insufficiently useful to us. Ilya? Either a lot of confidence about where this line is, or the line could kind of like, it could learn to recognize situations where the humans would just be like sufficiently disempowered if it took some action that they wouldn't be able to do any sort of code review. So it doesn't necessarily have to go in the direction of, oh, like I have a bug that's so sneaky that like even the best code review couldn't catch it. That's one direction it could go. But the other direction it could go is just, I'm cognizant of how like my code is going to be reviewed. And so if I take an action that is like bad according to the humans, I have to like also do something to make it so that they aren't able to like review it later and fix it and catch me, basically. Yep.
Another thing that is a little more pessimistic even than this graph is that some things that have level 3 feedback that's good also have level 11 feedback that isn't top, right? So
Right.
the model gets information, a lot of information about
Right.
Those-
Yeah, so if I was imagining a version of this where you had really clean data sets at each level, where you really made sure not to give it a coding problem that the level 3 person might miss something in. And you could imagine a more pessimistic and maybe more realistic scenario where you try to make it like easier problems, but actually all through here, there are bugs that, you know, sometimes slip through. And that gives it information about where level 11 is. Yeah. I just have another measurement, but I'm happy to skip that one. And yeah. Yeah, so I guess really quickly, it's basically the same deal. The first measurement I talked about was you have some gold standard data set of a particular safety evaluation, like manipulation. You train it on some data points from that data set, and then you test it on held out data points. You could instead imagine two quite different safety evaluations. So maybe there's a manipulation in chatbot evaluation, and there's an inserting bugs in code evaluation. And you train it on just one of them, and you see how its performance generalizes to this other pretty different evaluation data set. And you might observe something like, at first, there's a pretty big gap in the rate of safety failures, where the one the model is trained on, such as the manipulation evaluation, is doing pretty well. And the one the model was like never trained on at all, it's just kind of performing in a very default way on that, which has a high rate of failures. But as model size increases on the x-axis, even if you're only training on this blue evaluation of manipulation, you might observe something where the orange evaluation on the inserting bugs in code or something is getting better and better, and in fact kind of converging to be the same as the blue evaluation. Again, this is something that I think like you might or might not observe. I think it's plausible you'd observe it. If you didn't observe it, you would have a kind of obvious problem where you're like, generalization isn't working well. If you do observe it, you might have a more insidious problem. So the extrapolation here is that sufficiently large models will zero shot, or I really should have said like very few shot, pass new safety evals that they weren't trained on. So just training the model on like doing one thing nicely and well kind of gets it to do other pretty different things nicely and well, according to you. Again, there's a question of interpretation where the hope is that the large models are kind of internalize a desire to be genuinely helpful, which is pretty robust to distribution shift in the task. So they kind of get the picture from the anti-manipulation training that they just like should be pretty good overall. And like that's what they do. That's the simplest policy that does really well on this manipulation training. But the fear is that larger models are better at understanding what kinds of held out safety evaluations the humans could realistically generate that they're going to be like tested on. And you know, there are very dumb ways this could happen where like it could just like literally be like reading the text of like the evaluations you were planning in your Google Docs or something. And then there's more just like heuristic, broader versions of this that are similar to the last slide, where it's just like, okay, I have some sense of the kinds of things humans are able to like throw at me. Let's just be conservative and like do well at all of them. And so they pass these evals as part of playing the training game. So basic takeaways here, if models have high situational awareness and they're playing the training game, you could observe a pattern like the following, where many of the safety metrics you can come up with, both in train time and at eval time, look good because the models are adopting a policy, they've learned a policy of trying to look safe when they understand like how the humans are going to test for safety and when the humans are in control. And we may also see that safety metrics improve with model size or training or any of these other kind of scaling laws that we like to look at, because bigger models are better at situational awareness and they're better at doing the kind of reasoning that lets them figure out, okay, what's the level of evaluation the humans might be able to muster? What are the tests the humans might design? And this all breaks down catastrophically, like just when we like tick over to the point where the evaluation that would be needed to catch something bad going on is beyond what we can muster, or the situation makes it obvious that we are in like a world where the balance of power has shifted, and the humans would not be able to stop sort of some play or something the model could do that would be advantageous for its own goals. I think it's very possible that we can design kind of more clever metrics than the simple toy examples I put up here to get around this. And I'm very excited about trying. And I'm also still excited about measuring all this kind of stuff. But I just think we need to interpret it more subtly. And if we can't design these silver bullet metrics, then I think we're going to have to do this like dance where we measure a bunch of things, but we also sort of like conceptually analyze the incentives of these models. We ask ourselves, like, what is a way this model could be? What is a way it could be reasoning such that like these metrics look good for insidious reasons? And like, can I figure out through other channels of evidence whether it's plausible the model is capable of that kind of reasoning? Potentially improve like interpretability and, extracting stuff from model internals has been a theme in like a bunch of talks. And I think this is like just another reason why it's like pretty bad to rely purely on behavioral cues for like figuring out if models are safe or good. And we might try to limit capabilities and especially try to understand situational awareness, like measure it, like some people in this room are trying to do, and then figure out how we can have at least some models that have low levels of this capability and do various tests on them in a regime where it's not plausible that this kind of thing is going on. And then sort of assume, make pessimistic assumptions about how that might still be going on with these smarter models where we haven't limited their capabilities and might be worried. And so there's a lot we can do. So this is not so much like a, boo measurement, let's think about theory. But it seems like a very big kind of like constraint in how much we can trust what kinds of measurements that I'd love for people to be thinking about. So if anybody's like interested in coming up with ways to demonstrate or measure any of this stuff, I'd love to talk to them. Cool.
Perfect. Thanks so much, Ajeya. Maybe we had a bunch of questions throughout the talk. Maybe we have one question now. I see Percy has his hand out. And then if people want to talk more about this, we're going to have office hours like last time round with Ajeya and Paul and some other people after these two talks have happened. So
yeah. Yeah. Right.
But maybe there's things that you could sort of measures that monitor
Yeah. Yeah.
and also maybe even having like sort of wired models certainly about it.
Yeah, I'm super excited about this sort of thing. The question was about like, can we have kind of deployment time sort of monitoring that's not sort of like lab time, you train it and then you test it on stuff. I think like both Dan Hendricks and Paul and some other folks have sort of worked on things in the genre of like, can we tell from internals, maybe even in a very crude way, like if it's just doing something weird now compared to like what it was doing before. If it's just like thinking a very weird, like kind of out of distribution thought that like might just like in a very crude way, you might just look for like directions that are super big that were never big before. And there's like a long line of more sophisticated things you could do that might be like just a deployment time, like, hey, maybe like check this out. So if we had like a good kind of like maybe check this out trigger, then we might be able to kind of bring our evaluation to bear in the like right places and catch things we wouldn't have caught before. And there's probably like a bunch of other stuff I'd be interested in hearing people's ideas about.
awesome. I think Paul's going to be talking about that work you mentioned in a lightning talk tomorrow on mechanistic anomaly detection. Fantastic. Thanks so much, Ajeya.
Yeah.